The cosmos harbors forces so powerful they bend reality itself, pressures that could flatten entire worlds in an instant. Out there in the void, neutron stars squeeze more mass than our sun into a city-sized space, while black holes twist space-time into oblivion. These aren't just cosmic curiosities, they're the universe's ultimate extremes, where the laws of physics are pushed to their breaking point. Today, we're venturing into the heart of these unimaginable forces, uncovering 25 jaw-dropping facts about the most intense pressures in existence. From the crushing cores of collapsed stars to the violent births of galaxies, prepare to witness the universe's most breathtaking displays of raw power. Buckle up, this journey will change how you see the cosmos forever. Deep in the heart of a neutron star, matter undergoes a transformation so extreme it defies imagination. Picture this: an object so dense that a single teaspoon of its material would weigh billions of tons on Earth. These cosmic monsters are born from the explosive deaths of massive stars, where supernovas blast away outer layers while the core collapses inward. Gravity here is so intense that protons and electrons are forced together, merging into a sea of pure neutrons, a state of matter so exotic scientists call it neutron soup. The pressure inside exceeds 10 octillion pascals, enough to crush atoms into oblivion. That's like stacking 50,000 Empire State Buildings on top of a single grain of sand. Even light struggles to escape their grasp, warping the very fabric of spacetime around them. Neutron stars don't just bend the rules of physics, they rewrite them entirely. Step inside the realm of black holes, where gravity becomes so overpowering even light can't escape its clutches. At the edge of these cosmic voids lies the event horizon, a point of no return where the pull is so fierce it stretches and squeezes anything crossing it like taffy. Scientists call this gruesome process spaghettification, where tidal forces elongate objects into thin strands before they're crushed into oblivion. Picture a marble dropped into a cosmic trash compactor, first stretched impossibly thin, then compacted beyond recognition. At the black hole's heart lies the singularity, a point of infinite density where all known physics breaks down. Here, matter is compressed so violently that space and time cease to behave as we know them. It's the universe's ultimate pressure cooker, where the rules of reality are rewritten in ways we're still struggling to understand. At the very heart of our solar system, the sun's core operates like an unrelenting nuclear furnace, where mind-bending pressures sustain life as we know it. Here, temperatures soar past 15 million degrees Celsius, and pressures reach an astonishing 265 billion pascals. That's over 250,000 times the crushing weight at the bottom of Earth's deepest ocean trenches. In this cosmic pressure cooker, hydrogen atoms are squeezed together with such force that they fuse into helium, unleashing the energy that bathes our planet in warmth. Every second, 600 million tons of hydrogen vanish in this explosive dance, converted into light and heat through reactions more powerful than a billion atomic bombs. Yet without this controlled chaos, Earth would be a frozen wasteland, proof that violence and beauty often coexist in the cosmos. The sun's core doesn't just defy earthly expectations, it reveals how extreme forces can shape the delicate balance of life itself. When a star like our sun finally exhausts its nuclear fuel, it doesn't go out with a bang. Instead, it becomes something far stranger. The outer layers drift away, leaving behind a glowing ember called a white dwarf, where gravity battles an invisible quantum force in one of space's most delicate stalemates. These stellar remnants cram roughly the mass of our sun into a sphere no bigger than Earth, so dense that a single sugar cube of this material would outweigh an elephant. But here's the twist: despite this incredible crush of gravity, white dwarfs don't collapse further because of a bizarre quirk of physics called electron degeneracy pressure. It's like stuffing too many people into an elevator. At a certain point, the electrons simply refuse to be packed any tighter, pushing back with unimaginable force. Even the mighty gravity of a dead star can't overcome this quantum rebellion, but there's a limit. If a white dwarf grows beyond about 1.4 solar masses, what astronomers call the Chandrasekhar limit, this electron resistance fails catastrophically. The star can no longer support its own weight, triggering a runaway collapse that ends in a thermonuclear explosion so bright it outshines entire galaxies, a supernova. For those that avoid this fate, an even eerier destiny awaits. Over trillions of years, white dwarfs slowly cool into crystalline spheres of carbon, essentially becoming celestial diamonds floating in the void. Imagine entire stars turning into cosmic gemstones, their internal pressure frozen into perfect lattices that could outlast time itself. These stellar ghosts remind us that even in death, the universe finds ways to astonish. Among the most terrifying objects in the cosmos, magnetars rewrite the rules of extreme. These aren't just ordinary neutron stars, they're cosmic powerhouses wrapped in magnetic fields so intense, they'd strip the information from every credit card on Earth from halfway across the galaxy. Picture a magnetic force a quadrillion times stronger than our planet's, enough to distort the very atoms in your body if you dared to get too close. This unimaginable pressure doesn't just linger quietly, it violently reshapes the star itself, fracturing its crust in catastrophic starquakes. When a magnetar's surface cracks, it unleashes chaos on an astronomical scale. In less than a second, these starquakes release more energy than our Sun emits in 150,000 years, erupting in gamma-ray flares that outshine entire galaxies momentarily. One such blast in 2004 actually compressed Earth's upper atmosphere from 50,000 light-years away, a sobering reminder of their reach. The magnetic pressures inside are so extreme, they twist the fabric of space-time itself, creating ripples that physicists call magnetic mountains, distortions barely a millimeter high, yet dense enough to weigh as much as a mountain range. What makes these objects even stranger? Their magnetic fields are so powerful, they can heat the star's surface to 18 million degrees purely through magnetic friction. No nuclear reactions required. If you replaced the moon with a magnetar, its magnetic pull would liquefy every metal object on Earth while scrambling our planet's electromagnetic field beyond recognition. These cosmic anomalies prove that even in a universe full of extremes, some forces still push the boundaries of what we thought possible. At the very beginning of everything, before galaxies, before stars, even before atoms, the universe was a seething cauldron of unimaginable violence. The Big Bang wasn't just an explosion, it was the ultimate pressure cooker where forces so extreme they make neutron stars look gentle-shaped reality itself. In those first fleeting moments, pressures soared beyond 10 to the 100th power pascals, a number so vast it dwarfs the crushing weight at the center of every black hole combined. This wasn't just about raw force, it was a quantum battleground. Empty space itself rippled with violent fluctuations, particles blinking in and out of existence as energy transformed into matter and back again. The universe didn't just expand, it inflated, stretching from smaller than an atom to cosmic scales in less than a trillionth of a second. That explosive growth locked in tiny irregularities, the seeds that would eventually become galaxies and all the structures we see today. And here's the wildest part: for a brief moment, pure energy forged the first particles. Photons collided with enough violence to spontaneously create matter, fulfilling Einstein's famous equation, energy becoming mass under the most extreme pressures imaginable. Every proton, every electron in your body can trace its origins back to this primordial inferno, where the universe itself acted as the ultimate alchemist. The echoes of that pressure still resonate today, imprinted in the cosmic microwave background, a faint afterglow from when the cosmos was young, hot, and unimaginably dense. While stellar black holes are terrifying enough, supermassive black holes operate on an entirely different scale, galactic architects wielding power beyond comprehension. At the center of our own Milky Way, Sagittarius looms with 4 million times the Sun's mass, yet it's just one of countless giants anchoring galaxies across the cosmos. These behemoths don't merely consume matter, they shape the destiny of everything around them. The real spectacle unfolds in the accretion disk, a swirling maelstrom of superheated gas and dust spiraling toward oblivion. Temperatures here soar to millions of degrees as friction and gravity crush particles with pressures rivaling neutron stars. This chaos doesn't just feed the black hole, it births quasars, the universe's most luminous phenomena. A single quasar can outshine 1,000 galaxies, its brilliance powered by the sheer kinetic energy of matter being torn apart atom by atom. What's truly staggering is the reach of these gravitational titans. While their event horizons might span distances comparable to our solar system, their influence extends for thousands of light years, dictating the orbits of billions of stars. They're the invisible puppeteers of cosmic structure, proving that sometimes the most extreme forces in existence are also the quietest until they awaken. Beneath Jupiter's swirling storms lies a hidden world of unimaginable force where pressure transforms the very nature of matter. While its colorful bands rage with hurricanes larger than Earth, the real drama unfolds deep inside its core, where crushing forces reach 40 million times the pressure at sea level on our planet. This isn't just extreme, it's a laboratory for physics-defying phenomena. At these depths, something extraordinary happens to hydrogen, the universe's simplest element. Squeezed beyond recognition, the gas undergoes a metamorphosis, shedding its familiar properties to become metallic, a form so alien, it conducts electricity like copper while flowing like a liquid. Scientists believe this swirling ocean of metallic hydrogen generates Jupiter's monstrous magnetic field, 20,000 times stronger than Earth's. But here's the twist: Jupiter might have been destined for even greater extremes. Had it gathered roughly 80 times more mass, the pressure in its core could have ignited nuclear fusion, turning it into a second sun. Instead, it remains a failed star, a testament to how fine the line is between planet and star. Its storms, including the Great Red Spot, a centuries-old hurricane wider than Earth, are mere surface ripples compared to the chaos below. This gas giant doesn't just host extreme pressures, it's a cosmic pressure chamber, reshaping matter into forms we're only beginning to understand. Far beyond the realm of terrestrial storms, ice giants like Uranus and Neptune hide a spectacle more dazzling than any earthly weather, diamonds falling like rain. Beneath their frigid blue atmospheres, pressures soar past 8 million times Earth's surface level, crushing methane molecules into glittering crystal downpours. This surreal process begins when methane, a simple compound of carbon and hydrogen, plunges deep into the planet's interiors. The crushing force rips apart its molecular bonds, squeezing carbon atoms into tightly packed lattices while hydrogen escapes upward. What emerges isn't just tiny specks. Scientists predict these diamonds could grow as large as icebergs, sinking through slushy layers of ionized water and ammonia before settling around the core. Imagine standing in this storm, not water pelting your skin, but microscopic gemstones slicing through ultra-dense fluids at speeds rivaling bullets. Labs on Earth have recreated fragments of this phenomenon, using powerful lasers to mimic the extreme conditions for mere nanoseconds. But on Neptune and Uranus, this isn't an experiment, it's a perpetual cycle, where diamonds melt under even greater pressures near the core, only to rise and crystallize anew. Yet these worlds guard their riches fiercely. The very forces that forge these diamonds would instantly flatten any probe daring to reach them, a reminder that the universe's most dazzling wonders often lie just out of reach, glittering in the dark. Scientists have unlocked a window into the universe's birth by recreating its most extreme conditions right here on Earth. Inside particle colliders like the Large Hadron Collider, beams of lead nuclei smash together at nearly the speed of light, generating temperatures over 5 trillion degrees, 300,000 times hotter than the Sun's core. These collisions simulate pressures so intense they dissolve the very structure of matter itself, melting protons and neutrons into a seething primordial soup called quark-gluon plasma. This exotic state hasn't existed naturally since the first microseconds after the Big Bang, when the universe was too hot and dense for particles to stick together. Quarks and gluons, the building blocks of all visible matter, whirled freely in a plasma hotter than supernovas. Today, detectors at CERN capture this fleeting chaos in action, observing how the plasma expands and cools, allowing quarks to finally combine into the protons and neutrons we know. What's truly mind-bending? These experiments reveal that quark-gluon plasma behaves less like a gas and more like a perfect liquid, flowing with virtually no friction. It's a glimpse into the universe's infancy, where extreme pressures forged the first stable matter from sheer energy. Every atom in our bodies owes its existence to this violent cosmic alchemy, proof that sometimes to understand how everything began, we must first tear matter apart. Somewhere in the cosmos, planets exist where the very ground beneath your feet would melt before you could take a single step. Kepler 10b is one such nightmare world, a scorched wasteland where surface temperatures hit 1,600 degrees Celsius, hot enough to vaporize iron. But it's not just the heat that warps reality here. It's the crushing pressure, a relentless force 60 times stronger than Earth's, that keeps entire oceans of molten rock churning across its surface. Picture standing on this alien shore, except instead of water, waves of liquid lava stretch to the horizon, bubbling under an atmosphere so dense it behaves like both gas and liquid simultaneously. Scientists call this supercritical fluid, a state where the distinction between phases blurs into something truly alien. The skies themselves might rain molten silicate droplets, only to evaporate again before reaching the ground in a grotesque meteorological loop. The geology here defies earthly logic. With no tectonic plates to speak of, the entire planet could be one seething magma ocean, its crust constantly dissolving and reforming like the skin on a pot of boiling pudding. Any mountains that briefly solidify would quickly slump back into the molten abyss, their peaks no match for the overwhelming pressure from above. These lava worlds are nature's ultimate crucibles, proof that when conditions grow extreme enough, even rock forgets how to be solid. In August 2017, the universe performed its greatest alchemy show, a cosmic collision that answered questions we'd been asking for centuries. Two neutron stars spiraled toward each other in a galaxy 130 million light-years away, their final orbits distorting spacetime so violently that they sent ripples through the cosmos. When they finally collided, the impact released pressures so unimaginable that they forged entire oceans of gold, platinum, and other precious metals in mere seconds. This event, dubbed GW 178017 by astronomers, wasn't just a light show. The gravitational waves it produced shook detectors on Earth, while telescopes caught the fiery aftermath glowing brighter than a billion suns. But the real magic happened in the debris, where extreme pressures transformed ordinary neutrons into heavy elements through a process called rapid neutron capture. Picture a nuclear reactor running at cosmic scales, atoms bombarded by so many neutrons so quickly that they swell into gold, platinum, and uranium almost instantly. Here's what's truly humbling: the gold in your wedding ring, the platinum in your electronics, they likely originated from violent mergers like this. These cataclysms are nature's ultimate foundries, scattering their metallic creations across galaxies to be recycled into new stars, planets, and eventually us. Every time you hold a piece of jewelry, you're holding stardust forged in the universe's most extreme crucible. At speeds approaching light, the universe plays tricks with reality that would make even the most seasoned physicist pause. When an object accelerates to these extreme velocities, Einstein's theory of relativity kicks in with bizarre consequences. Space contracts, time dilates, and matter itself warps under forces we might call effective pressures. Imagine a cosmic ray particle racing through space at 99.999% the speed of light. To a stationary observer, this particle wouldn't just appear flattened like a pancake. It would experience its own mass increasing exponentially, as if an invisible hand were pressing down with impossible weight. This isn't just theoretical. Cosmic rays, mostly protons traveling at near light speeds, routinely slam into Earth's atmosphere with energy surpassing anything our most powerful particle colliders can produce. At these velocities, the effective pressures generated are so intense that collisions create showers of secondary particles, each carrying a fragment of that insane kinetic energy. Some scientists speculate that if a macroscopic object like a spaceship ever approached such speeds, relativistic effects would compress it like an accordion, front to back, while tidal forces threaten to tear it apart atom by atom. And then there's the tantalizing possibility of warp drives, concepts that bend spacetime itself to circumvent light speed limits. The catch: the energy required would generate gravitational pressures capable of crushing entire star systems. It's a sobering reminder, in the race toward light speed, the universe erects barriers not just of energy, but of raw, distorting force, where the very act of moving fast enough reshapes reality around you. In the vast cosmic tapestry where crushing pressures dominate most celestial objects, there exists a realm of eerie nothingness, the Boötes void, stretching an incomprehensible 330 million light-years across. This cosmic desert contains so little matter that its pressure verges on absolute zero. Imagine a space so empty, if the Milky Way sat at its center, we wouldn't have discovered another galaxy until the 1960s. This staggering void isn't just a curiosity, it's a mystery that defies our models of the universe. While most regions teem with galaxies clustered like glitter, the Boötes void holds only a handful, scattered like lost islands in an endless ocean. The near-total absence of matter means gravity's grip here is almost non-existent, allowing dark energy, the enigmatic force accelerating the universe's expansion, to dominate unchallenged. What baffles scientists most is how such a void could form. Did some ancient cosmic event clear this region, or does its existence hint at gaps in our understanding of structure formation? Voids like Boötes aren't mere empty spaces, they're laboratories for studying the universe's most elusive ingredient, dark energy. In these ghostly expanses where pressure drops to almost nothing, the cosmos whispers secrets about the forces shaping its ultimate fate. When a massive star reaches the end of its life, it doesn't fade quietly, it detonates in a cataclysm so violent it outshines galaxies. The true spectacle unfolds in the star's core, where pressures skyrocket to 10 raised to the power of 44 pascals, a number so vast it could squeeze entire planets into specks. This is the stellar forge where elements heavier than iron are born, and the process defies everything we know about physics. As the core collapses, it doesn't just give in to gravity. It rebounds with unimaginable force, sending a shockwave racing outward at 1/10 the speed of light. That rebound isn't just an explosion, it's the universe's ultimate pressure cooker. Atoms are bombarded with neutrons so rapidly they can't stabilize, swelling into heavy elements like gold, uranium, and platinum in mere seconds. The Crab Nebula's swirling remnants are a frozen snapshot of this chaos, filaments of gas infused with these forged metals, glowing eerily across the cosmos. What's truly astonishing, without these explosions, the periodic table would stop at iron. Our world, our bodies contain atoms that could only exist because dying stars shattered themselves in these bursts of extreme pressure. Every piece of jewelry, every ounce of lead shielding, even the calcium in your bones, traces its origins back to the white-hot heart of a supernova, where the universe literally presses matter into existence. While galaxies glitter like islands in the cosmic dark, an invisible architect weaves their fate, dark matter, the universe's hidden scaffolding. This mysterious substance exerts a gravitational pull so immense it bends entire galaxies to its will, yet it refuses to interact with light, making it nearly undetectable. But here's where things get stranger. Dark matter doesn't just tug on stars, it might be pressing them into shape with quantum forces we're only beginning to understand. Take the Bullet Cluster, a cosmic collision that handed scientists undeniable proof. When two galaxy clusters slammed together, their visible gas clouds screeched to a halt, heated by friction. But the dark matter kept racing ahead, detected only by how its gravity warped the light of distant galaxies. This wasn't just a ghostly presence, it revealed how dark matter's gravitational pressure molds the universe, herding stars and gas into the structures we see today. Efforts to unmask this elusive substance range from ultra-sensitive detectors buried deep underground to telescopes hunting for distortions in the cosmic microwave background. Some theories suggest dark matter particles might generate a subtle quantum pressure, influencing galaxy rotation in ways ordinary gravity can't explain. Picture an invisible hand sculpting the cosmos, pushing stars into spiral arms, pressing clusters into filaments, all while remaining frustratingly just out of reach. Until we catch it in the act, dark matter remains the universe's most powerful phantom, shaping everything while revealing almost nothing. In the cosmic ballet of destruction, few performances rival the deadly dance of binary stars locked in each other's gravitational grip. Take Air Scorpii, a white dwarf and red dwarf whirling so close that their orbital dance lasts just 3.5 hours. The forces at play here don't just bend the rules, they shred them. As these stellar partners spin, tidal pressures stretch their atmospheres like taffy, stripping gas from the red dwarf and funneling it toward its white dwarf companion in a luminous river of superheated plasma. The stream glows white-hot as it spirals inward, accelerated to nearly a third the speed of light before slamming into the white dwarf's surface with the energy of 1 billion atomic bombs. But the spectacle doesn't stop there. Aer Scorpii's white dwarf spins so fast, completing a full rotation every 2 minutes, that it transforms into a cosmic lighthouse, blasting the surrounding space with beams of radiation powerful enough to ionize gas halfway across the solar system. Every pulse rips through the red dwarf's atmosphere like a solar flare on steroids, creating a feedback loop of stellar violence. And in the end, their dance can only conclude one way: a cataclysmic merger. Over millennia, gravitational waves will sap their orbital energy, drawing them closer until the red dwarf is torn apart entirely, consumed by its denser partner. These binary systems are nature's most extreme pressure chambers, stellar partners doomed to a spectacular embrace, rewriting the night sky with their final, fiery collision. HD 189,733b isn't just another exoplanet, it's a vision of cosmic fury that makes even the most vivid sci-fi hellscape seem tame. This deep blue world, orbiting perilously close to its parent star, harbors winds that scream across its atmosphere at 7,000 miles per hour, 6 times the speed of sound. But the real nightmare lies beneath those howling gales, where atmospheric pressures reach levels so extreme they transform minerals into vaporized glass, raining sideways in a glittering, lethal storm. Unlike Earth's gentle raindrops, the precipitation here is molten silica, particles of sand superheated until they become tiny shards of glass, whipped horizontally by hurricane-force winds. The planet's cobalt hue, initially mistaken for serene oceans, actually comes from clouds of silicate particles scattering light, a beautiful facade masking unimaginable violence. Even more startling, the temperature gradient between its scorching day side and cooler night side is so steep it fuels these hyper winds, a thermal engine of destruction running non-stop. Science fiction often depicts hellish worlds, but HD 189,733b surpasses them all, no fire and brimstone needed. Here, nature's raw forces sculpt a landscape where the very air is weaponized and the sky rains shattered glass. It's a chilling reminder that the universe doesn't need mythical demons to create realms of pure extremity. It already has physics. The universe isn't just a random scattering of galaxies. It's woven into an intricate cosmic web, with threads of dark matter and gas stretching across unimaginable distances. And embedded in these vast filaments are ghostly echoes from the dawn of time itself, ripples known as baryon acoustic oscillations. Imagine tossing a stone into a primordial pond 14 billion years ago, only for the ripples to freeze in place, preserving the exact moment of that first splash. These oscillations began as pressure waves racing through the superheated plasma of the infant universe, condensing matter into dense peaks and sparse valleys. When the cosmos cooled enough for atoms to form, those waves froze in place, imprinting a pattern into the distribution of galaxies that still lingers today. Astronomers now use these fossilized ripples as a cosmic ruler. Each wave crest spaced roughly 500 million light-years apart, allowing them to map the universe's expansion with stunning precision. What's truly astonishing, without dark energy's influence, these oscillations would have faded eons ago. Instead, they've stretched as the universe expands, carrying a record of both its explosive birth and its accelerating fate. Every time we chart a new galaxy cluster, we're not just mapping space, we're reading vibrations from the Big Bang itself, etched into the cosmos like grooves on a cosmic vinyl. In the catastrophic final moments of a massive star's life, an invisible force plays the most crucial role, one carried by particles so ghostly, they pass through entire planets like they're not even there. Neutrinos, those nearly massless cosmic phantoms, become the star's executioners and sculptors in its dying breath. When a stellar core collapses, 99% of its energy doesn't explode outward in light. It escapes as a tsunami of neutrinos, trillions upon trillions streaming through the star's outer layers in milliseconds. But here's the twist: despite their reluctance to interact with matter, this neutrino flood is so unimaginably dense it exerts real pressure, like trillions of tiny fingers pressing outward against the star's collapsing shell. That neutrino wind, traveling at near light speed, becomes the ultimate shockwave driver, transferring just enough momentum to blast the star's outer layers into space. We're seeing the fingerprints of this process in supernova light, curves, the telltale brightening that occurs when shockwaves finally reach the surface, often delayed by hours as neutrinos work their invisible magic. Detectors like Japan's Super Kamiok have actually captured these neutrino bursts from dying stars, recording the precise moment when a distant supernova's core collapses. In 1987, scientists spotted 24 neutrinos from SN 1987A, a whisper from a star that died 160,000 years ago. What seems like a tiny number is actually a staggering revelation. Those few particles represented a flood of 10 octillion neutrinos washing over Earth, most passing through unnoticed. This neutrino pressure doesn't just destroy, it creates. The shockwave it helps generate cooks up heavy elements in its wake, scattering stardust that will eventually form new planets and life. Next time you feel sunlight on your skin, remember, the very atoms in your body were likely forged by a star's death, propelled into the cosmos by ghostly particles you'll never see or feel, until one day, perhaps, another supernova's neutrinos silently pass through you unnoticed. If wormholes exist, they'd be the universe's ultimate shortcuts, tunnels stitching space and time together in defiance of every law we know. But holding one open would demand something even stranger than the wormhole itself, a substance with negative pressure, pushing outward when everything else in the cosmos crushes inward. This isn't just rare, it's a full rebellion against physics as we understand it. Einstein's equations hinted at the possibility long before sci-fi embraced it. Theoretically, an Einstein-Rosen bridge could connect two distant points in spacetime like a cosmic hallway, but without exotic matter, a hypothetical material with negative energy density, the tunnel would snap shut instantly, crushed by its own gravitational forces. Picture trying to keep a vacuum hose open against the weight of an elephant. Now imagine that elephant is space-time itself collapsing, the strangest part. Negative pressure doesn't just resist collapse, it actively warps space-time outward, countering gravity's pull. Some theories suggest quantum fields might produce fleeting bursts of this effect, but scaling it up to stabilize a traversable wormhole would require energies beyond anything we've ever observed. Even if we could harness it, the side effects could be catastrophic, from tidal forces shredding matter to time dilation, twisting causality into knots. Yet the allure persists. From blackboard equations to blockbuster movies, wormholes captivate because they represent the ultimate. What if a backdoor through the universe's rigid rules? For now, they remain locked in the realm of theory and speculation, waiting for someone or something to crack the code of negative pressure and turn cosmic shortcuts into reality. Until then, they're a thrilling reminder of how much we still don't know about the fabric of reality. The universe has its own heartbeat, a rhythm so precise it puts atomic clocks to shame. Born from the ashes of supernova, pulsars are nature's ultimate lighthouses, spinning at dizzying speeds while hurling beams of radiation across the cosmos like cosmic strobe lights. Take the Crab pulsar, a stellar remnant at the heart of a shattered star. 30 times a second, it whips around, flinging out pulses of energy so regular you could set your watch by them. If your watch could survive radiation blasts powerful enough to vaporize planets. What fuels this relentless ticking? A neutron star's unimaginable density, squeezed so tight it spins faster than a blender blade. As these stellar corpses rotate, their magnetic fields trillions of times stronger than Earth's, whip charged particles into frenzy, accelerating them near light speed. The result, twin beams of X-rays and gamma rays shooting from the magnetic poles, sweeping space like a celestial searchlight. Every time one of those beams crosses Earth's path, we detect a pulse, a fleeting flash from a corpse that refuses to fade quietly. The Crab pulsar's rhythm wasn't always this steady. When Chinese astronomers recorded its parent supernova exploding in 1054, the newborn pulsar spun 60 times faster, a frenetic newborn slowing gracefully over centuries. Today, its pulses arrive with metronome precision, each one carrying the echo of a star's violent death and the eerie order that emerged from chaos. These spinning sentinels don't just mark time. They're clocks set by the universe itself, ticking in the dark long after their creators have gone. There exists a pressure so extreme, it marks the boundary where physics itself breaks down. Known as the Planck pressure, 4.63 times 10 to the 113th power pascals. This staggering value represents the ultimate ceiling of what the universe can theoretically withstand. To grasp this absurd magnitude, imagine stacking every black hole in the observable universe onto a single atom. You still wouldn't come close. This isn't just an abstract number. The Planck pressure defines the point where gravity stops playing by quantum rules and becomes indistinguishable from the other fundamental forces where spacetime itself might dissolve into a froth of quantum uncertainty. Only two events in cosmic history might have brushed against this limit. The instant of the Big Bang, when all existence was compressed into an unfathomably dense point, and the singularities at the hearts of black holes, where matter is crushed beyond any known physics. Yet here's the twist: we'll likely never observe or recreate these conditions. The energy required to reach Planck pressure would demand a particle accelerator larger than our galaxy. Even nature reserves this extreme for moments of ultimate transformation, when the fabric of reality is either born or reborn. It's a humbling reminder. The universe holds realms of extremity so vast they exist just beyond the edge of human comprehension. Hidden in the quantum fabric of our universe lies a theoretical doomsday mechanism so absolute it could rewrite reality in an instant. Scientists call it vacuum decay, a catastrophic phase transition where the very ground state of existence shifts beneath our feet. Picture the Higgs field, that invisible energy matrix giving particles their mass, as a marble resting in a valley. Our universe enjoys stability because that valley is deep, but what if there's a deeper valley elsewhere in the quantum landscape? A chance quantum fluctuation could nudge the Higgs field over the cosmic ridge, triggering a bubble of true vacuum that expands at light speed. Inside this bubble, the laws of physics would rewrite themselves, erasing atoms, forces, and even spacetime as we know them. The shockwave's leading edge would be a wall of pure energy, annihilating everything without warning, a cosmic off switch pressed by nature itself. Yet before panic sets in, consider this: the odds are astronomically low. The Higgs field has likely sat in its current state for 13.8 billion years without collapsing. Experiments at the Large Hadron Collider suggest our vacuum is stable enough to outlast every star in the sky. But the terrifying beauty of this scenario lies in its physics, not its probability. Vacuum decay isn't about fiery explosions or black holes. It's about the universe quietly redefining existence in its own language, a silent reminder that even the vacuum of space hums with unimaginable potential energy. So while we search for cosmic threats from asteroids or solar flares, the most profound danger might come from nothing at all, an emptiness so unstable it holds the power to unmake everything. Thankfully, the same research probing this apocalyptic scenario also helps us understand why the universe has lasted this long and why it might just keep going. While the universe wields unimaginable pressures as everyday tools, humanity isn't content to merely observe. We're learning to recreate them. In laboratories that seem ripped from science fiction, scientists are bending the laws of physics to harness the same forces that power stars. At California's National Ignition Facility, 192 of the world's most powerful lasers converge on a peppercorn-sized fuel pellet, subjecting it to pressures exceeding 300 billion atmospheres, briefly mimicking conditions at the core of our sun. The goal: controlled nuclear fusion, the holy grail of clean energy. Just as stars fuse hydrogen into helium under extreme pressure, releasing colossal energy, NIF's experiments aim to spark self-sustaining reactions here on Earth. Their recent breakthroughs have inched tantalizingly close to ignition, where fusion output surpasses the laser energy input, a watershed moment heralding a potential energy revolution. Meanwhile, halfway across the globe in France, the ITER tokamak takes a different approach. This donut-shaped behemoth uses magnetic fields 100,000 times stronger than Earth's to confine superheated plasma at 150 million degrees Celsius. Instead of lasers crushing inward, ITER superconducting magnets create an invisible bottle where charged particles spiral endlessly, fusing under sustained stellar pressures. What makes these projects extraordinary isn't just their technological audacity, it's the promise they carry. Fusion could offer limitless energy without greenhouse gases or long-lived radioactive waste turning seawater into fuel. The challenges remain daunting, but every shot at NIF, every pulse in ITER plasma brings us closer to taming the cosmic forces that light the stars. After billions of years, the universe's most extreme pressures might finally become humanity's greatest power source, proof that by daring to replicate the heavens, we may secure our future on Earth. From the crushing embrace of neutron stars to the unfathomable pressures at the birth of the universe, we've journeyed through extremes that defy imagination. These 25 facts reveal more than cosmic curiosities. They show how pressure sculpts the very fabric of reality. It forges stars in stellar furnaces, crystallizes diamond rain on distant worlds, and even births the gold in your jewelry from neutron star collisions. Every layer of the cosmos, from the quantum foam of vacuum decay to the eerie silence of cosmic voids, tells a story written in force and compression. What unites these phenomena isn't just their intensity, it's their role as architects of existence. Without the universe's relentless pressures, there'd be no galaxies, no planets, no elements to build life itself. So next time you feel under pressure, remember, it's nothing compared to the universe. If you've enjoyed this dive into cosmic extremes, hit like and subscribe for more journeys to the edge of science. The cosmos still holds countless mysteries, and we're just getting started. Until next time, keep looking up. You never know what wonders might crush your expectations.